parametric surfaces and their areas. Recall that we described a space curve by a vector function of a single parameter t earlier in the course. When you use a single parameter, you get a simple space curve. When two parameters are used, you get a surface in space. These surfaces are called parametric surfaces. The function r is going to be a function that has three component functions, x, y, and z, and each of these component functions will be a function of two parameters, which we commonly call u and v. This is a vector valued function defined on a region D in the uv plane. So x, y, and z, the component functions of r, are functions of the two variables u and v. And again, this defines a parametric surface S in R3. And these equations, x, y, and z, are called the parametric equations of the surface. Let's consider the following example. Identify and sketch the surface with the vector equation r of uv equals 2 cosine u as the first component, v as a second component, and 2 sine of u as the third component. I prefer to use this notation, but you can leave it in this notation if you want. So now we need to try to find relationships between x, y, and z. Now we know that cosine squared of u plus sine squared of u is always equal to 1. And from the parametric equations, we know that cosine of u is equal to x over 2, and sine of u is equal to z over 2. So if I plug these expressions into the trigonometric identity here, we're going to come up with x over 2 squared plus z over 2 squared is equal to 1, or x squared plus z squared is equal to 4. And there are no restrictions on the variables u and v, and so this would essentially be a cylinder in R2. Now what about the variable y? Y is simply equal to v, and that means that y can basically be equal to any number. So if we attempt to sketch this, we have a circle in the xz plane, so that is going to look something like this. And then y can be any variable, or any number, So what we're going to get here is an infinite cylinder, which looks something like this. Now here is a slightly better picture of that infinite cylinder. And I want to point out that if you were to impose some restrictions on the parameters u and v, for example, if u can only be a value between 0 and pi over 2, since u is representing the angle from the positive x-axis toward the positive z-axis, if u is restricted between 0 and pi over 2, this would only give us a quarter of this cylinder. Furthermore, if v is between 0 and 3, that means that y will only be a value between 0 and 3, and so that restricts the length of this cylinder. So we can get different curves even from the same equations by simply imposing restrictions on our parameters. Something that is very helpful when graphing parametric surface is something called grid curves. A grid curve is when you consider u and v and you hold one of the variables constant. So for example, I might hold the variable u constant, and then we look at all the possibilities for v within that domain. So we get this vertical line here. That line is going to map over into the parametric surface as what is called a grid curve. We can also hold the variable v constant and let u vary in the domain, and that will give us another grid curve kind of going in the opposite direction there. And if you graph lots of these grid curves, such as what I'm doing here, what you'll see is that you start to see the shape of the surface when you sketch those curves, right? We could do the same thing with the other direction here. If I draw grid curves the other way, we're going to start seeing this thing trace out here. And in fact, a lot of software uses grid curves to help sketch the graph of these parametric surfaces. So as an example, use a computer to graph the surface r of uv is equal to this vector function. And then which grid curves have u constant and which ones have v constant. So first of all, look at the intricacy of this surface. It's quite complex, and this would be quite difficult to graph and understand without having these lines, right? These grid curves. So let's think about which ones are which. So if u is constant, the vector function r could be thought of as 2 plus sine of v times some constant, 2 plus sine of v again times another constant, and then some constant, I'll call it m plus cosine of v. So does that correspond to the long lines you see here or the lines that are wrapping around it? The easy way to understand this is the value of z is bounded, right? So like for a particular constant m, the value of z is only going to be m plus cosine of v. And since we know cosine varies between 1 and -1, whatever the value of m, this z value cannot be much more or much less than that value of m. So u must be these curves here, these curves that are sort of circular and wrapping around this tube. And so now if v is constant, then you're going to have a constant times cosine, a constant times sine, and then a constant plus u. And notice for this, z can pretty much be any value, and then the x and y values are going to be a multiple of sine and cosine. So that is definitely something that is a more circular pattern in terms of x and y. And so if v is constant, that would be these long lines here. Next, let's find a vector function that represents the plane that passes through the point P0 with position vector R0 and that contains two non-parallel vectors A and B. If we think of the initial point P0 as being the terminal point of a vector in standard position, then we can basically think of the point P0 as being R0. Now, the key is, how do we get all the other points in the plane? Well, if you're given two non-parallel vectors, A and B, to go from the vector P0 to the vector P, all one needs to do is add a multiple of the vector A to a multiple of the vector B. So if I have the vector A here, for example, I might have to multiply that by something, and then multiply the vector B by something. And if I add those two together, I'll end up at P. So for the plane here, R is going to be the vector R0 plus some parameter U times the vector A plus some parameter V times the vector B. So if we think of the vector R0 as having coordinates x0, y0, z0, and the vectors A and B having coordinates, as you see here, then any vector R having coordinates x, y, and z, where x, y, and z is a point on the plane, would have to satisfy this equation. That means that x would have to be equal to x0 plus u times a1 plus v times b1. Y has to be y0 plus u times a2 plus v times b2. And z has to be z0 plus u times a3 plus v times b3. And so anytime we have two non-parallel vectors, a and b, and a point on the plane, we can always write the parametric equations for that plane as follows. In the next example, we want to find a parametric representation of the sphere x squared plus y squared plus z squared is equal to a squared. So that is simply a sphere whose center is at the origin and whose radius is equal to a. Well, this is a perfect situation to simply use the spherical coordinates. So remember, the spherical coordinates are x is equal to rho, which in this case is a times the sine of phi cosine of theta. Y is equal to a times the sine of phi sine of theta. And z is equal to a times the cosine of phi. Now remember, a in this case is a constant. So the parameters here are phi and theta. Now how do we get the sphere? Well, remember, theta is the angle that goes in this direction. So to get the entire sphere, we have to make a full revolution here. So theta has to be between 0 and 2 pi. But phi is the angle from the positive z-axis, and that only needs to go from the top of the z-axis down to the bottom. Because once we do that and we rotate all the way around, we get the entire sphere. So theta needs to be between 0 and 2 pi, and phi must be between 0 and pi. So we can give the parametric equations like we have here, or we can write this as r is equal to a sine phi cosine theta, a sine phi sine theta, and a cosine phi. Next, let's find a parametric representation for the cylinder. So we have x squared plus y squared is equal to 4, and z is between 0 and 1. So anytime you have the equation of a circle, we could always use sine and cosine to parameterize that circle. So we know that x is going to be 2 times the cosine of theta, y will be 2 times the sine of theta, and theta will be between 0 and 2 pi. And then z just needs to be a value between 0 and 1. And so z can simply be itself. And then we would just impose the restriction that z be between 0 and 1. So we don't always use the letters u and v to be our parameters. And in fact, sometimes we'll use the variables themselves to be parameters. And again, we can always write that in vector form. And down below, we have a little diagram of the domain for theta and z, and then the image under this vector function, which of course is a cylinder. Next, we want to find a vector function that represents the elliptic paraboloid z equals x squared plus 2y squared. Now, there's a couple of different ways that we can do this, but basically anytime z is represented as a function of x and y, you could parameterize it very easily by simply letting x equal x, letting y equal y, and then z will equal x squared plus 2y squared. And so the vector function here would simply be x, y, and then x squared plus 2y squared. And of course, just to bring it up, we also could use the component notation. Right? So as you know, I prefer this notation, but both of these are valid. And also, it's worth noting that anytime z is a function of x and y, we can use this parameterization. So we can let x be x, y be y, and then z will simply be f of xy. In the next example, we wish to find a parametric representation for the surface z equals 2 times the square root of x squared plus y squared. And that is the top half of the cone z squared equals 4x squared plus 4y squared. So of course, one way to do this is I could simply let x be x, and I could let y be y, and then z would just be the 2 times the square root of x squared plus y squared, which of course could also be represented as a vector function. So again, these are the parametric equations, and this is the vector function. But this is not the only way to do this problem. Consider trying this. What if I used polar coordinates? What if I let x be equal to 2 cosine theta, y be equal to 2 sine of theta, and we know that z squared is 4 times the quantity x squared plus y squared, so we could say that z is 4 times r squared, z squared is 4 times r squared. Therefore, z would simply be the square root of 4r squared, which is 2r. And so another representation could be r equals 2 cosine theta, 2 sine theta, and then 2r. Now, theta, of course, would be between 0 and 2 pi, but then r would only be greater than 0, greater than or equal to 0, because we only want to get the top half of the cone. So it's actually good to have options. Sometimes you might prefer one parameterization, and other times another parameterization might be more easy to work with. Now let's consider surfaces of revolution. Let's go back to 2-variable calculus just for a minute. Suppose we have some function f of x, and we revolve that function about the x-axis. We know that this is going to create some kind of a 3-dimensional shape here. And we can do all kinds of things with this. One of the things we can do is we can look for the surface area of this thing. So notice that the surface that you see here is very similar to the surface you see over here in the XYZ coordinate system. So if I'm given some value x on the x-axis, let's say that corresponds to this value right here, f of x can be thought of as sort of like being a radius of this object. So in 3 dimensions, notice that that radius f of x does not necessarily have to be directly above the x-axis. It rotates all the way around the x-axis. So f of x is the radius of this object. And you can see that that point on the surface there is going to have some kind of a z coordinate over here and a y coordinate over here. Now, if theta is the angle through which it has been rotated, we can see that the z coordinate here is simply going to be f of x times the sine of theta. And that's just using right triangle trigonometry. And then the y-coordinate would be this distance here. This distance corresponds to the y-axis. And so the y-coordinate would be f of x cosine of theta. And then the x-coordinate would just be x. And so we can parameterize this surface by letting x equal x, letting y equal f of x cosine of theta, and letting z equal f of x sine of theta. Or as a vector function, simply x, f of x cosine theta, f of x sine theta. And of course, in this case, x would be between a and b, and theta would have to be in between 0 and 2 pi to get one full revolution. So let's find the parametric equations for the surface generated by rotating the curve y equals sine of x, x between 0 and 2 pi about the x-axis, and then use these equations to graph the surface of revolution. And so we know that we're going to use these equations. And so x is going to be x, y is going to be the function, which is sine of x, multiplied by cosine of theta, and z is going to be the function sine of x, multiplied by sine of theta. And we know x has to be in between 0 and 2 pi, and theta also needs to be in between 0 and 2 pi. And so let's think about what this would look like. It's easiest to do this if we just go back to the original coordinate system where x and y are here, and then you could think of z as being an axis like this, a little bit different than what we normally do. But we know the curve y equals sine of x looks like this. And that's from 0 to 2 pi. And if we rotate that around the x-axis, we're going to get a mirror image like this, and it will be three-dimensional in nature. So it's going to look something like this. And I'll bring in a little better picture. There it is. And actually, my picture is not too bad, but this one's nice. It has grid lines, etc. Now let's talk about finding tangent planes to a parametric surface. Suppose we have a vector function defining a parametric surface in R3, and over here we have our domain in the UV coordinate system. And over here we have a point P naught on the surface, and we want to find the tangent plane at that point. So first of all, let's realize that there is a grid line that we can draw here by holding one of the variables constant, and a grid line that we can draw here by holding the other variable constant. So if we hold u constant, this grid line would be a grid line representing u being constant. And along that grid line, there are lots of tangent vectors that we could draw. Of course, we want to look at the tangent vector at the point P naught. So that tangent vector would be as follows. It's just the partial derivatives of x with respect to v, of y with respect to v, and of z with respect to v, evaluated at the point u naught v naught, and then multiplied by their component vectors. If we hold v constant, now u is free to vary. There's lots of tangent lines along that grid line. We want the tangent line at the point P naught. So the tangent line, we're going to call that RU. And it is found the same way, taking the partial derivatives of x, y, and z with respect to u, plugging in the point, and then multiplying by their component vectors. Now, to get the equation of a plane, the easiest way to do that is to simply find the normal vector to the plane. And the normal vector would have to be perpendicular to both of the tangent vectors. So the normal vector is perpendicular to RV, and the normal vector is perpendicular to RU. So one possible candidate for the normal vector would simply be the cross product RU with RV, because we know that when we take the cross product of two vectors, we get a vector that's perpendicular to both. So we can find the equation of the tangent plane by simply finding that normal vector, which is nothing more than the cross product of these two vectors. Let's take a look at an example. So here we want to find the tangent plane to the surface with parametric equations x equals u squared, y equals v squared, and z equals u plus 2v. So first we need RU, and this is going to be the partial derivative of x with respect to u, the partial derivative of y with respect to u, and the partial derivative of z with respect to u. And if we compute these, we're going to get 2u, 0, and 1. And then we need RV, which is simply the partial derivative of x with respect to v, the partial derivative of y with respect to v, and the partial derivative of z with respect to v. And if we do that, we're going to get 0, 2v, and 2. And now the normal vector to our plane will simply be RU crossed with RV. And so that is the cross product of these two vectors. And I think I will spare you of the work this time. So if we take the cross product, we're going to get negative 2v, negative 4u, and 4uv. All right. So now to get the normal vector to the plane, we need to take the normal vector at the point 113. Now the point 113, that's x, y, and z. Okay, so x, y, and z we know is equal to 113. And we know that x is equal to u squared, and so this means that u squared has to be 1. We know that y is equal to v squared, and so v squared has to be 1. And then we also know that z is equal to u plus 2v, and that means u plus 2v must be equal to 3. Now, if you think about the possibilities here, u can be plus or minus 1, v can be plus or minus 1, but then we have to plug in a combination of u and v that makes this true. So clearly this means that u must be 1 and v must be 1. And so now our normal vector here at the particular point is going to be this vector, but we have to plug in u and v both equal to 1. And so that's going to give us -2, -4, and 4. Now for the normal vector, remember, you can use any vector that is parallel to this vector. So if you see a common multiple that you want to divide by or a negative that you want to factor out, we can go ahead and do that. So we can use the normal vector 1, 2, -2. So all I'm doing here is I'm just dividing each of these by -2. Now we know that if we take that normal vector and we take the dot product with any point r on the plane, that is going to equal the normal vector dotted with the particular point on the plane. So what we have is the vector 1, 2, -2 dot product with x, y, and z must be equal to 1, 2, -2 dot product with the point on the plane, which is 1, 1, 3. So this is x plus 2y minus 2z must be equal to 1 plus 2 minus 6. Or x plus 2y minus 2z must be equal to -3. Now, as a definition, if a smooth parametric surface S is given by the equation R here, that's a vector equation, and S is covered just once as u and v ranges through a particular domain, then the area of that surface is the double integral of RU crossed with RV. Now, why is this? This is true because RU crossed with RV is the area of the parallelogram formed by those tangent vectors. And we talked earlier about how that parallelogram can be used to approximate the patch on the surface. So I'll spare you the details here. We've already discussed that in an earlier video. I think that was the change of variables video. And we'll go ahead and do an example. So find the surface area of a sphere of radius A. So first thing we need to do is come up with a parameterization for a sphere, but we already did that earlier with spherical coordinates. So now we need to get r phi and r theta. And these are going to be formed by taking the partial derivatives with respect to phi and then with respect to theta. So the partial derivative of x with respect to phi is going to be a cosine phi cosine theta. The partial derivative of y with respect to phi is going to be a cosine phi sine theta. And finally, the partial derivative of z with respect to phi will be negative a sine of phi. Next, we take the partial derivative of x with respect to theta. That's going to be negative sine of theta times this. So that will be negative a sine phi sine theta. The partial derivative here with respect to theta will be a sine phi cosine theta. And finally, the derivative with respect to theta here is going to be 0. And so now we just want to take the cross product of these two vectors. And again, I'll spare you the details here. And so now we just need to take the cross product here. So I'm going to spare you the details on this. Let's go ahead and write that down off camera. All right, and there it is. Now we need to take the magnitude of this. And so that is simply the magnitude of this vector, which is going to be pretty big. It's going to be the square root of the squares of all of these added together. So if we square this, we're going to get a to the fourth, sine to the fourth, cosine squared, etc. And let's go ahead and write that down. And now with this expression, we can factor out a to the fourth out of all three, and we'll pull it outside the radical, so that is going to become an a squared. And then on the inside, we can factor out some things as well. Notice out of the first two terms here, we can pull out sine to the fourth of phi, and then we have cosine squared theta plus sine squared theta, which is really nice because that's equal to 1. Then we have plus sine squared phi, cosine squared phi. All right, so like I said, this is equal to 1, so this is going to go away. And then we can pull out a sine squared of phi. That's going to come out of here and here. So what will be left over after that is another sine squared of phi, and then plus cosine squared of phi. But again, this is equal to 1. So we end up with a squared square root of sine squared of phi, which is a squared times the absolute value of the sine of phi. But we know that phi is going to be, phi is going to be in between 0 and pi, and sine of phi is positive already on that domain. And so this is equal to a squared sine of phi. So now to get the surface area, we just need to take the double integral of this cross product, d phi d theta, and then we have to know our limits. So let's remember that theta ranges from 0 to 2 pi, and phi ranges from 0 to pi. And so the a squared we can pull out completely. We have the integral from 0 to 2 pi of d theta, and the integral from 0 to pi of sine of phi d phi. And this is going to be a squared times theta from 0 to 2 pi times negative cosine of phi from 0 to pi. And this is a squared times 2 pi times, and then over here, we've done this before, but if you plug in pi, you get negative 1. Negative 1 is 1. And then when you plug in 0, you get minus 1 again. And so that is 2. And so this ends up being 4 pi a squared. Now remember, a was the radius of the sphere. And so what that basically says is the surface area of a sphere is 4 pi times the radius squared. And that is the formula for the surface area of a sphere. Now for the special case of a surface S with equation z equals f of xy, where xy lies in some domain D and f has continuous partial derivatives, we can take x and y as parameters and use the parametric equations x equals x, y equals y, and z equals f of xy. And so if I want to get the surface area, I need to get Rx and I need to get Ry. And so Rx is going to be 1, 0, fx of xy, and Ry is going to be 0, 1, fy of xy. And now if we take the cross product of these two vectors, we are going to get negative fx xy, negative fy xy, and 1. And keep in mind that, this is just the partial derivative of f with respect to x, and this is the partial derivative of f with respect to y. I like to mix up my notations, so that's what this is here. And now if we take the magnitude of this cross product, this will be the square root of fx squared plus fy squared plus 1 squared. Or we can write this as the square root of 1 plus the partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared. Or we could even write this as the square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared. Both of these notations are the same, of course, because we know that z is equal to f of xy. But then that says that the surface area is nothing more than the double integral over the domain D of the square root of 1 plus this and then dx dy. And this is a very similar surface area formula that you might remember from Calculus 2. So now let's find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So here is that paraboloid. Here's z equals 9. So we want to find the surface of this thing here. So to do this, we need to go ahead and compute our partial derivatives. The partial derivative of z with respect to x is 2x, and the partial derivative of z with respect to y is 2y. So this surface area will be the double integral of the square root of 1 plus 2x quantity squared plus 2y quantity squared dx dy. Now, we could integrate with respect to x and y, but the domain down here is circular, and so the limits would be a little bit complicated to do that. It's probably better that we use polar coordinates. So let's rewrite this. We can say that this is equal to the double integral of the square root of 1 plus, now this is 4x squared and this is 4y squared. If we factor out the 4, we get 4 times the quantity x squared plus y squared dx dy. Now, of course, we know that x squared plus y squared is r squared. And so if we convert this over to polar coordinates, we'll have the square root of 1 plus 4r squared. And then don't forget, when your dx dy switches over to polar coordinates, you get r dr d theta. R needs to go between 0 and 3, right? Because if it lies under the plane z equals 9, that corresponds to x and y equals 3 down below. Now for that, all you have to do is plug 9 in for z. And you can see that this is simply a circle of radius 9. So that's why we need those limits. And then, of course, theta has to be between 0 and 2 pi. This is a relatively simple integral. In fact, we can separate the r's and the thetas since they are separable. And then this integral right here, of course, is just going to be 2 pi. And this integral here, we need to do a little u substitution. Okay, and there is that u substitution there. So we have 2 pi, and that's going to be multiplied by 1/12 multiplied by 37 radical 37 minus 1. And we can simplify that just a little bit more. We could say this is pi over 6, 37 radical 37 minus 1. And that concludes this video lesson.